Today we're going to look at section 3.3, which is the beginning of our polynomial functions. And so the first thing we're going to do is define what a polynomial is, its notation, so we can kind of learn the language that we're going to use to describe other things. So a polynomial basically just means, poly means many, nomial means terms, so it just means many terms. Some of the polynomials that you may have heard in the past, you had the binomial from Algebra 1, which means there are two terms. The trinomial means you had three terms. The monomial, you had one term. So a polynomial is many terms. So since I can have as many terms as I can even conceive of, we can't use, like in Algebra 1, you used ax squared plus bx plus c. That's too many letters. We don't have enough letters. So they have adopted this notation. Don't panic. This a sub n values, these n minus 1 and so forth, just stand for a number, which are called coefficients. They are real numbers. They're in front of every single term of the polynomial. And they just represent, like I said, a constant, a real number. And the subscript just tells you where it goes. So this number is the number in front of the x to the n. You'll notice that the subscript value is the same as the exponent of this term. And that's all it is. It's just a place identifier. The exponents, you'll notice, also decrease by 1. So it's like when you write it in standard form, a polynomial is the highest exponent, then the next highest, then the next highest, and all the way down to the term without an x variable. These integers, these exponents are non-negative integers. So none of them will be negative, and they'll only be integers. The number that is in front of the x term with the highest exponent, so a sub n, is called the leading coefficient. It doesn't mean it's the one in front. It means it's the number that is associated with the highest exponented term. So if this is all jumbled around and not written in proper order, no matter where it lands, it's still the leading coefficient. So it doesn't have to be first, although in standard form, it will be first. A sub 0 is with the term, the x term that has x to the 0, which is 1. So a sub 0 is called the constant. It is the term that does not have an x variable with it. And then the number n, which represents the largest exponent, then that is called the degree. So they classify polynomials by degree. In Algebra 1, you had linear functions where the exponent on the x was 1. You had quadratics where the highest exponent is a 2. You had cubics where the highest exponent was a 3, and so forth and so on. So after a certain value, they just call it by the highest exponent. So polynomials of degree 5, polynomials of degree 6. These are all little groupings of those types of polynomials. So we want to learn these terminology because this is how they describe different processes later on. Once the polynomial is in standard form, we can tell a lot about the polynomial, about the graph of the polynomial, just by looking at the equation. So by looking at an equation, what is that graph going to look like? What kind of characteristics does it have? These are some things you want to know also. Number one is, I know the y-intercept is whatever the constant is. Because a y-intercept has an x value of 0, so if I plug in 0 for all these terms with an x in it, the only term that's left is the constant term, so that's the y-intercept. Some things you might not know, but now you will, that the graph can have no more than n minus 1 turns. So if a polynomial is a degree 5, then I know it can't have more than 4 turns in the graph. And we'll talk more about the graph here in just a minute. I also know that the graph can have no more than n x-intercepts. So the graph cannot touch the x-axis more than the degree. It can cross less, but it can't cross more. So the highest number of x-intercepts you can have is n. And again, you may not have that many, but you can't have more than that number. The other one we want to talk about is a thing called end behavior. Okay? The end behavior. What happens on the ends of this graph? And I'm going to show you the leading coefficient test. This picture is also in your textbook on page 183. You'll see a leading coefficient test. But here's basically what it is, and I'm going to pull this away so you can see the whole thing. So polynomials basically turn around, up and down, stuff like this. And so when you look at this, you'll see that in between is dotted because I don't know how it looks. I just made something up. But I'm interested on the ends, the two end pieces. Okay? Do they both go down? Do they both go up? Does one go down, one go up? And can I look at the equation, determine how that's going to happen? And the answer is yes. That's the leading coefficient test. The leading coefficient test, once you learn it, you will know how to describe how the ends behave. And so it's broken down into two things. You got to know two pieces of information. You have to know the highest exponent or the degree, and you have to know the leading coefficient. Is the leading coefficient positive or negative? And so it breaks it up into four pieces. What happens if the degree is even? So if the highest exponent is an even number, like 2, 4, 6, 8, then I know, based off of just that alone, that the two ends of the graph, so the left end and the right end, will do exactly the same thing. They'll either both go down or they'll both go up. So I know that for a fact. So how do I know which way they're going to go? That's where the leading coefficient comes in. The leading coefficient, if it is negative, means it's going to go down. And if it's positive, that means they're going to go up. Now, where have we seen this before? Well, in pretty much all transformations. This a sub n plays the same role as when the outside number on our, here, let me show you an example. So if I gave you a negative 2x squared, that is basically the leading coefficient, and we notice that it's negative. Well, if it's negative, then we have a reflection across the x-axis, meaning the graph gets flipped over, so it has to point down. So that's what's going on. And if it's positive, then the graph just goes in its normal upward progression. But what if the degree is odd? If the degree is odd, you'll notice that one side will be going up and the other side has to go down. So again, how do I know which way? Well, the leading coefficient tells me. If the leading coefficient is negative, again, then I have a reflection. This time it would just be x to the third. That means it reflects over the x-axis. Well, in a normal x to the third graph, the right side goes up. So because this is negative, I know the right side will be going down. And then because of that, then I know then because of an odd degree, the left side had to go up because it had to do one up, one down. Over here, if the leading coefficient is positive, then I know that the right side goes up. So then because it's an odd degree, the left side had to go down. So how do we describe these? Well, there's two ways to do it. One is your textbook's way. They're going to use what's called a limit description. And so I'm going to show you this with the limit description. But really, there's another, if you're having trouble with that one, we can talk about another possible way that you can write it. Very similar. I know it's hard to read this, so let me zoom in a bit and show you the notation. So in this example right here, the right side of this graph is going up and the left side is going up. And this function I called p of x. So you'll notice it says the limit. Well, let's talk about what's going on here. So in a number line situation, as I move to the right, the x values are going bigger and bigger and bigger. So the x's are going to infinity. And you'll see that displayed right there. Well, as the x goes to infinity, what is the y values? Well, the y values are, in this case, I called it p of x. So the y values are p of x. Well, what are they doing? Well, they're just continuing going upwards, so they're going to positive infinity also. So as the x goes to the right, the y values go up. That's what it means. So this notation says exactly the same thing as this statement right here, which is the alternate way that you can write it if you choose to do so. Okay? So the limit means, so as x goes to infinity, so the extreme possible outcome as x goes to infinity of the y values, so what's the highest y value I can ever get? And, well, they go up, so to forever, so we just call that infinity. So that's how that works in the connection between the two different statements. I would prefer that you use the limit notation for future reference because that's how they use it beyond this class. Okay? So intuitively, the right side is going to go up, the left side is going to go up. To display the left side, you're going to use negative infinity. So the left on the x-axis is negative, the right is positive, up is positive, and down would be negative. So if you look over at this one, you can see that's a notation. The limit as x goes to infinity, that means the right side the y values goes to, oh, I didn't put the negative there, negative infinity. The limit as x goes to negative infinity of the y values, negative infinity. So that's how you would write that out. Another thing we want to look at when we look at, so that's the leading coefficient, the end behavior. Some other things you'll be asked to do as part of the characteristics of these, because these numbers, these polynomials have these terms, then we have established these local extremas. Now, we talked about this before. There's actually a video in your Google Classroom that shows you how to use the calculator to find those. So we want to find what's called the local extrema. The local extrema, which is plural from maxers and mins, or otherwise known as relative extrema. The highest point on the curve in an interval around this point is a local max. So basically, a peak. So when I have a term that peaks, then there's a point up here called the local maximum. When I have a point that dips, then there's a point here at the bottom, which is the lowest point, and that would be considered a local minimum. Sometimes it'll use the word relative. It means the same thing. So local or relative maximum or local relative minimum. Maximums, minimums, and you will use a calculator to determine these. Sometimes, you can't read it, let me zoom in a little bit more. Sometimes a graph will have what's called an absolute max or min. An absolute max or min means, in this example right here, this point is the lowest point for the entire graph. That becomes then an absolute minimum, or if it was the other way around, an absolute maximum. It is also, because it's in the valley here, a local min. So it's a local min, but more importantly, it's an absolute minimum for the entire graph. Notice this graph right here has no absolute max. A graph does not have to have an absolute max nor an absolute min. Here's an example right here. It has a local minimum, has a local maximum, but there is no absolute minimum and no absolute maximum because these arrows continue on forever. So there is no value up there that you can consider to be the highest or the lowest. So that is absolute maxes and mins. Okay, and that's what I described right here in the definition. An absolute max or min, the highest or lowest point on the entire domain of the function. For polynomials, the domain is the entire real number line. So all real numbers is the domain for all polynomials. And then what I just said also, a function does not need to have any local or absolute extrema. Okay, and we're only going to find these using a calculator. And again, there's an actual video in your Google Classroom that shows you how to use and find the extremas on the calculator itself. The next thing of importance are the zeros of a polynomial function. What are the zeros? The zeros of a polynomial function are the value or values, because you can have more than one, of x, that when you substitute that value into the polynomial for x, you will get a y value of 0. So that's what the zeros are. How do I find them? Well, there's a couple of ways to do it, and we're going to spend much of our time in this unit talking about how to find these zeros, both on the calculator and without a calculator. So on the graph of a polynomial function, the real zeros are the x-intercepts, because those are where the y value is equal to 0. When the graph touches the x-axis, the y is a 0 value. So these points right here would be considered the zeros of a polynomial that looks like that. This one has 4. There are 4 zeros for that one. Okay, so we're going to learn how to find those. Another way to do it is we can find the zeros by solving the equation. So we can take the polynomial, set it equal to 0, and solve it, which is a technique we're going to use quite often. For right now, all you have available to you is really for quadratic stuff, or your factoring techniques with GCF, if that's possible. I'll show you an example here in a little bit, but we have to use factoring techniques at this time. The number and type of zeros also tell us about the shape and behavior of the graph of the polynomial function. So notice up here I'm talking about real zeros. Well, there's also other kinds of zeros. There are things called complex zeros that also tell us about the shape and behavior of that graph, and we'll go into that a little bit more detail later. For this lesson, we're going to focus on the real zeros. Sometimes a polynomial can have more than one zero. That's the same. It's called a multiplicity. So if I factor something out, let me show you an example of what I mean by that. If I have, let's just take a simple one, a polynomial y equals x plus 2 squared, then what happens here, and we all know from transformations that I'm going to move this two units to the left. The normal polynomial is at 0, so this one's going to be over here at 2, negative 2, and it basically looks like this. Well, a repeated 0, okay, we're talking about this. So I can take this, I can set it equal to 0, which means I have x plus 2 squared equals 0. Well, this means x plus 2 times x plus 2 equals 0. So I have the same thing twice. So this, by solving this right here from Algebra 1 techniques, we get x equals negative 2 and x equals negative 2. The same answer twice. So when I look at a polynomial and I want to know if it has a repeated 0, look at the behavior. Since there are 2 answers that are repeated, that's even, you'll notice that the graph touches at negative 2 and then turns around and goes back up. This is what happens with repeated zeros that repeat an even number of times. If it repeats an even number of times, the graph will come down and touch the curve and turn, like so. So if it repeats, if I have 2, if it repeats 4 times, 6 times, 8 times, the graph will come down and touch the curve, either from the top or from the bottom. It can come from the bottom also, and turn. But what if it does a repeating an odd number of times? So that would be the one where I had 3 of these. Then that graph, when you do it, is going to go through, and it's going to have a slight bend, okay, a slight bend at that point. So if you see a slight bend right there on the x-axis and going through, that is an idea that it could be an odd multiplicity. And so you want to look at it and see whether or not that's actually occurring. Again, we'll explore this in much more detail as we get moving along. But that's what's happening. Multiplicity, repeated zeros. Okay? The last thing I was going to bring everything together before I do some examples. And this part down here is the part I want to talk about. Here's the basic fundamental connections that we want to know. You need to know these because this is how we're going to do most of our work. How we get all of our stuff done is this concept right here. If I have a polynomial function f and a real number k, the following are equivalent. That means they mean exactly, they lead into each other. You're talking about the same thing from a different point of view. So if that's the case, and I say x equals k, and I tell you that's a solution, okay, of this equation, f of x equals 0, then I've also told you that k is a 0 of that function. And if k is real, then k comma 0 is the x-intercept of the graph of that function. And then this one right here is very important right here. And I told you that x minus k is a factor of that polynomial. And we use this quite a bit. And this is how we actually learn how to factor polynomials beyond your Algebra 1 level material. Knowing that if I can find a 0, then I can find a factor using that technique. This plays a major role in how we find zeros in the polynomial, so we definitely want to make sure we learn these. Now, I have a little bit of time. I'm going to show you some examples of what your homework might look like. And here we go. So the first one I want to do is show you how to do the in behavior and extrema. I'm going to look at problem number 25 from your textbook. And here's what it looks like. They give you f of x equals 3x to the fourth minus 5x squared plus 3. And so the textbook asks you to describe the in behavior. So I don't have to graph this thing. I can tell you right off the bat what the in behavior is, because all I'm looking for is the leading coefficient and the degree. The leading coefficient is 3. So in other words, a sub n, the leading coefficient, is positive, because that's all I care about if it's positive or negative. And I know that the degree, which in this case is the highest exponent, I know that the degree is even. So because of that and the leading coefficient test, I know even and greater than 0, that both ends will go up. So here's how you describe it. The limit as x goes to the right, positive infinity, of this function called f of x, the end is going to go up. So as the x values get bigger, the y values get bigger also. This is the one from the right. The limit as x goes to the left of this function, the y values are also going up. So that is how you would write your in behavior. That is the in behavior. For the extremas, we need to graph. So I'm going to graph this on the calculator. And again, the technique, I'm going to go fairly quickly here, but the technique is shown in the video in your Google Classroom. So we're going to, that's not what I want. And we're going to graph, and I'm going to type that in. 3 times x raised to the 4. When you do an exponent beyond 2, use the exponent button. You got to make sure you get out of the exponent to type in the rest. Minus 5x squared. If you just use the squared button, it will actually drop it back out automatically. Plus 3. I'm going to graph that. So there's the graph that I see. Okay. You can zoom in if you need to see bigger amounts, which I'm going to do. I'm going to zoom this in a bit. Window, I'm going to zoom in. I'm going to center it right about here so I can see everything a little bit more clearly. So, menu, analyze the graph, number 6. And then over here, I get zeros, min, max, and intersection. I'm looking for minimum. You get the dotted line. Move to the lower bound. That means move it to the left of where you think you have a minimum. Select. It now says upper bound. Slide across, and the dot will appear. When the dot appears, select to end the calculations, and there is your point. So that is the minimum at that point right there. You want the x value, and you want to round it to 3 decimal places. So I have a relative min, or a local min, when x equals a negative 0.913. So a local minimum at x equals that. On the graph, you would graph and label both points, both parts, the x and the y. So you'll be asked to graph polynomials and identify the local max or min on the graph and label those. Okay. You can also label it over here if you wanted to. You have a local min. Another way that it's acceptable to write, you have a local min at the point negative 0.913, comma, and then 0.917. So you can write it that way also. Okay. I would define the zeros on this one, but as you can see from my graph, I do not have any x-intercepts, so there are no real zeros. Just a little peek into the future there. This right here is an example where you would have what's called complex zeros. This is what it looks like if you have complex. But we'll talk more about that at a later date. Let's look at another one. Let's look at problem number 36. In problem number 36, I have a function x to the third minus 25x. And in this case, it asks you to find the zeros algebraically. So the only algebraic technique that you have that will help you with this is factoring. So this is a factoring problem. Your goal is to factor this completely, and then we're going to set it equal to 0. So the technique for finding this is using this concept that I showed you over here. If I want to find the zeros, if I can factor it, then I can pull the zeros out of the factors. This is the technique you use in Algebra 1. You factored a polynomial completely. Okay, you set it equal to 0. So x to the third minus 25, x equals 0. And we solve this for the zeros. And so first thing I do is factor out the x because it's common. And now I have that. And then you should notice that this right here is the difference of 2 squares. And so you can factor that. Still equal to 0 into x plus 5, x minus 5. So what I have here is a product of 3 numbers that equal to 0. So one of them, if not, has to be a 0. So we set each of these equal to 0 and find the values that make them 0. And we call those your zeros. So these are the zeros because they are the solution to the equation when we set it equal to 0. So that means these are the zeros of the function. So as I have written it right here, I have described the solutions. To write them as zeros, you simply write zeros and list them. 0, and you can list those two as plus or minus 5. So these are the zeros. These are the solutions to this equation. And if I graphed it, then I would have, these are the x coordinates, the x part of the points on the x-axis. So that's how that works. And the last one is, again, using this connections that we have, 53. And in 53, I tell you that the zeros are 3, -4, and 6. And says, using algebra, find a cubic, that means a degree 3 polynomial with these given zeros. So because they told me it's a cubic function already, then I don't have to do anything special. Later on, we'll learn how to do it a different way, a more intense way. So because I know there's only going to be 3 zeros for a cubic, remember cubic means x to the 3, and we can have no more than that many zeros. The graph can have no more than n x-intercepts, or zeros. And if I told you n is 3, then I can't have more than 3. So what I'm doing in this case is I'm going in reverse. If I do factoring technique to get to zeros, if I give you the zeros, I go backwards through factoring to get back to the original function. So that means my original function in factored form, because these are zeros, I know that x minus that 0 is a factor. So x minus 3 is a factor. X minus a -4 is a factor. And x minus 6 is a factor. And that's all of them. And so then you can actually find the polynomial in standard form by multiplying this stuff out. So this one right here, I usually do the second two first. This is x squared minus 6x plus 4x minus 24. And then combine like terms, minus 2x minus 24. And then multiply by these two things. I'll get x to the third minus 2x squared minus 24x minus 3x squared plus 6x plus 72. They're all jumbled up. You want to write it in standard form where the highest exponent is first. So we need to rewrite and combine like terms. There's x to the third. It's the only one. I have these 2x squared terms, minus 5x squared. I have these two x terms. So this will be minus 18x, and then plus 72. That is the polynomial that has those zeros. So this is the cubic polynomial that has those zeros. And if you graph this on the calculator, you will see that it goes through those points. Let's see if I can do it real quick. So if I graph this down here, so x to the third minus 5x squared minus 18x plus 72. And if I graph it, you'll see that it goes through -4, it goes through +3, and it goes through +6. So I get the glare out of there for you. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4. So there you go. And we're going to be doing more of this together, but that's the end of the video.